Section 7.2, Part 2, Volumes by the Disc and Washer Method. You can see I have a couple of washers here. That will be something we use in a little bit. A disc. Believe it or not, this quarter is actually a very, very thin disc. And if I take a bunch of discs and stack them on top of each other, I kind of get a pyramid of a shape. And if I really looked at what I had there, there's a bunch of discs. Okay, someone's colored on the side of them, I think. With each one of them being, now, to stay on this thing, they had to have a hole in it. But each one of these is a disc, and it has a thickness, and we have a shape, and here is an axis that something has been, a rectangle has been revolved around. So here's a representative rectangle. If I put that rectangle on an axis of revolution, and I revolved it real quickly, so quick that you could see, I would eventually get, as you can see, a disc. That disc has a thickness, and this rectangle here, as I revolved it, made my disc become a circle. Now, in geometry, what was the volume of this one little slice? Well, it was the area of the base times the height. Well, if my sizes of my disc are not changing as I go along the axis of revolution, then my solid is just a cylinder and I don't need calculus. But if the size of that disc is changing, let's say I'm looking here at my stack of coins, there's a quarter, a nickel, a penny, and a dime. Each one of these is a different size. But I could find the volume of the solid created by revolving that representative rectangle around an axis of revolution and adding up all those infinite slices. And you can see that I could be looking at something like this. Okay? And that is called a volume of revolution. So another way to create a solid having known cross sections is to revolve a region in the plane about a line called the axis of revolution, producing a solid of revolution. When this is done, the cross sections perpendicular to the axis of rotation are circular. Again, my axis of rotation, when I revolve that representative rectangle, I get the disc. It's a circular disc. Okay, so we want to show that representative rectangle. Now, since the points of the function become the radii for the cross sections, remember each cross section is going to be a circle. Again, how do I find the volume of this one slice? It is the area of the base times the thickness of the slice. This little bitty single disc, but we're going to change sizes. So each one's got a different size, but not when I go and write my formula. Okay? So the points of the function become the radii for the cross section. And the area of the cross section as a function of x is, well, we know the area of a circle, pi r squared. And this time, what is our r? Our r is that radius that's making that solid. And how are we finding that radius? Well, in the disc method, one end of the rectangle is on the axis of revolution and the other one is going up to whatever the function is that is in our plane. So if our cross sections are perpendicular to the x-axis, our volume is pi from a to b, f of x quantity squared dx. Integrate with respect to x. My limits of integration are the x-axis. The slices, my representative rectangle slices, are cutting up or slicing up the x-axis. If my slices are on the y-axis, guess what? I'm going to integrate from c to d, and my function has to be a function of y squared. So we'll look at that in class. But let's look at an example. Find the volume of the solid that results from revolving the region under the curve y equals square root of x about the x-axis over the interval from 1 to 4. First, we want to sketch the function y equals square root of x, and we want to shade the region that's from 1 to 4, and we want to put our slice in there. So here is our function, y is the square root of x. I want to integrate from 1 to 4 and shade that region, and here is my representative slice, because that slice is my radius. So my radius is going to be found by a function of x, because I'm at 0 here, and I'm going up to the function. So my radius is from 0 up to here, which is f of x, and my function is square root of x. How do I find that volume? Remember, we are finding pi times r squared times the height. Pi r squared, that's the area of the base, times the height is your dx. Pi from a to b, r squared dx. My r is square root of x, so pi from 1 to 4, square root of x squared. Square root of x is x. This is ready to fundamental theorem. And we get 15 pi over 2 units cubed. There you go. It's just that easy. Not too terrible. Okay. Now, what happens when my region is more complex, like something like this one? Look at that. Got stuff going on there. All right, so each one of these is a really big washer. And back in geometry, what did you learn how to do when you had a cylinder and you had something taken out of the center? How did you find the volume of that? You took the volume of the big one minus the volume of the little one, right? Well, we're going to do the same thing. The volume of the big one is going to give us our big radius, so big radius squared. The volume of the little one is going to involve little radius squared. And that's really the only change. So when a region is enclosed by two functions f and g with f of x greater than or equal to g of x, neither one being the axis of rotation, the resulting cross-section is a washer. To find the area of a washer, subtract the area of the smaller circle from the larger one. Let capital R represent the larger radius, so from the center to this would be your big R, and let little r be represent the smaller radius, again from the center, which is your axis of rotation, up to that function there. So area would be the area of the big disk minus the area of the smaller disk. And this is going to be easier if we actually factor out the pi and do big radius squared minus little radius squared. So if our washer is perpendicular to the x-axis, my volume is going to be pi from a to b, big radius squared minus little radius squared d. So if my cross sections are perpendicular to the y-axis, so my volume is pi on the integral from c to d, f of y squared minus g of y squared dy. So big radius with respect to y squared, little radius with respect to y squared. Okay, so we know what the sine of x looks like. The square root of sine x is just going to flatten that curve a little bit. We still have the maximum to be 1. We're on the interval from 0 to pi. And if I take this slice right here and bring it out here, thinking about rotating around, notice I draw the arrow, I'm rotating around the x-axis. I'm going to get this disk. We know that length, that is our thickness, that's our dx part. And what is our radius from the axis of revolution up to the curve? So let us remember, the volume of this disk is pi r squared h. Big R because there's only one R. Little r is 0 because our rectangle is actually sitting on that axis of revolution. So in this case, little r is 0. Big R goes up to the function. So first of all, identify our big R. And we're on the interval from 0 to pi. And so if I look at that representative slice, that is dx, that is big R. What is my volume? Pi from 0 to pi, r squared h. See that? Volume is pi from 0 to pi r squared h, where h is that thickness of the slice. And so that's going to give us from 0 to pi, pi times sine of x dx. We know how to anti-differentiate that. Gives us a negative cosine. That negative sign right there is just an accident waiting to happen. So let's go ahead and factor it out of that pair of parentheses. Now we do our fundamental theorem, substitute our values in, find the cosine of pi and 0, do the proper work, and we get 2 pi units cubed. Let's remember, units matter. Also, every answer you get should be positive because we are finding a volume. All right, we're going to look at number 2. Rotate the region enclosed by y equals x squared, y equals 0, and x equals 2 about the x-axis. Identify the shape and the solid formed and determine its volume. By the way, this right here looks like a chocolate-covered egg or maybe a lemon drop. Okay. All right, let's look at this one here. We are looking at y equals x squared about the x-axis enclosed by y equals x squared, x equals 2, and the x-axis. Here's our representative rectangle. If we pull that out and look at our slice, again, volume is pi r squared h. The little r is actually 0 because once again, our rectangle is sitting on the axis of revolution. Very important to draw that. What is our radius? It's going up to the curve, and the curve is y equals x squared. So our radius is x squared. Our limits of integration are from 0 to 2. And now we're ready to go. Volume is pi from 0 to 2, x squared squared dx. That gives us x to the 4th dx from 0 to 2, which anti-differentiates to x fifth over 5. I went ahead and pulled the 5 out. And we're going to evaluate it, and we get 32 pi over 5 units cubed. Now, what does this look like if we revolve it this way? How about a Hershey's Kiss? Kind of, a little bit. And I'm not going to do the next problem. We will do it in class, but I do want you to make these corrections if they're not already in your lecture manual. This should be y equals 1/2 x minus 1, x equals 0, y equals 0, and the line y equals 2. Identify the shape of the solid formed when this region is revolved around the y-axis, and then determine its volume. And we will look at the other problems on this page and the next in class. So your TP for this section, out of the text, numbers 1 and 3. See you next time.